Hello, welcome to my Lab 5. I'm Matthew Mazzatano. So today I'll be discussing an experiment, principles used within that, computer programs like Tractor and Glow scripts, which I use to make to analyze the video and create a model, the results from that, and the meaning behind it. So, for my experiment, I observed the motion of this slinky as it is let go from rest. As you'll see, the slinky has an odd pattern of motion. The bottom of the slinky does not move while it is in free fall. So, to get on with the experiment, too far. I uploaded this video into Tractor. So using Tractor, I found the height of this man in order to gauge the distance that the slinky falls. The slinky weighs 0.2 kilograms. I set the origin to be where the slinky hits the ground. I tracked the movement of the bottom of the slinky. That's important. So I was really my focus during this experiment was on the bottom of the slinky. The video is at 300 frames per second. Okay, so moving into my simulated model using Glow script, I used the Lab 2 starter code to model the falling spring since it models an object in free fall. Alright, so onto my code for Glow script, I inputted the mass of the slinky, which I am calling the ball. It's the bottom of the slinky was at 0.513 meters off the ground, and it had a 0 initial velocity. And here I am updating the time, gravity. So the force of the spring I have is equal to the negative of the force of gravity, and the force of gravity is negative mass times gravity in the direction of j hat. Okay, so while the time is less than 0.437 seconds, 0.437 seconds is the time at which the slinky fully collapses, and at which point the slinky begins to move downwards, the bottom of the slinky. So F net is equal to the force of gravity plus the force of the spring, which means that on the bottom of the slinky, the force of gravity is acting on it, pulling it downwards, and then the force of the spring is pulling it upwards, which is why it stays suspended. And I update the velocity in the position of the bottom of the slinky. Moving on into my next while loop. This time interval is the time in which the slinky has already collapsed and is beginning to fall under the force of gravity. And I update the velocity and the position. So here's my graph of the motion of the bottom of the slinky. We see that it stays stationary, not moving, up until 0.43 seconds, and then begins to fall due to the force of gravity. Quickly note that at the end it is not at 0 meters. It is at the bottom of the slinky is at 0.194 meters off the ground. Here are my graphs from Tractor. So this is the top of the spring, seeing a pretty much constant velocity as it falls, and also similar motion as we saw in the graph above from the Glow script, looking at the bottom of the spring. Okay, so as seen in the live video, the bottom of the spring remains motionless in midair due to the force of the spring until the rest of the spring collapses and no longer resists the force of gravity. The top of the spring's change in position versus change in time, its velocity was relatively constant, talking about this graph right here. And something I noted was that the simulated model doesn't reach the ground, y equals 0 meters. It only reached y equals 1.94 meters, and I think this is due to that the top of the spring, as it collapses onto the bottom of the spring, that collision imparts an unaccounted for boost in velocity, which is not modeled in my simulated model, which is why the bottom only reached 1.94 meters off the ground at the end of my time interval. So what the result means is, like, essentially the whole purpose of this experiment was to observe and model the odd behavior of that fallen slinky. The bottom of the spring was under the effect of the downwards force of gravity as well as the upwards force of the spring. This caused the bottom of the spring to remain motionless and float in midair. Once the spring had fully collapsed and no longer provided that upwards force, the bottom of the spring began to fall due to the force of gravity until it hit the ground. Okay, thank you. That's all.